Periodic variation in physical properties. So in Chapter 7 we discussed the shielding effect. The presence of other electrons in the atom reduces the electrostatic attraction between the given electron and the positively charged protons in the nucleus. So the valence electrons are shielded from the attraction of the nucleus by the core electrons. The effective nuclear charge, or Z sub EFF, is the nuclear charge felt by an electron when both the actual nuclear charge, Z, and the repulsion effects, or the shielding, of other electrons are taken into account. So then we have this little formula. The effective nuclear charge equals the actual nuclear charge minus sigma, which is your shielding constant or screening constant. Now that constant is greater than 0, but always less than Z. So if we look at helium, for example, helium has a +2 charge and has 2 valence electrons. When it has both of its electrons, it takes 3.94 times 10 to the negative 18th joules to remove the first electron. But once that first electron is gone, the remaining electron has lost its shielding, and so it takes 8.72 times 10 to the negative 18th joules. It takes more energy to remove that one electron because it's less shielded. So core electrons shield valence electrons much more than valence electrons shield one another. So as you're moving across period 2, the added electron is a valence electron, and the valence electrons do not shield each other as well, so the net effect is greater effective nuclear charge felt by the valence electron. But when you move down a group, the valence electrons are now added to an increasingly larger shell, because N is increasing. The electrostatic attraction between the nucleus and the valence electron actually decreases because there's more shielding. So atomic radius. Many physical properties, including density, melting point, and boiling point, are related to the size of the atoms. Atomic radius is 1/2 distance between 2 nuclei and 2 adjacent metal atoms or in a diatomic molecule. In other words, atomic radius is the size of the atom. As you go across a period, the effective charge is increasing, so the atomic radius is actually decreasing. So as we move across a period, the atom is actually getting smaller because the valence electrons are being added to the same energy level, and the effective charge is increasing, so they're getting pulled closer to the nucleus. But as you move down a group, the effective charge is decreasing, so the atomic radius is actually increasing. As you go down a group, those valence electrons are being added to a higher energy level, which expands the radius of the atom. Here's a graph of atomic radiuses, radii, and if you look at the top points of each line, that would be our group 1. Notice that the group 1 element is always going higher than the previous one. As you move down a group, the orbital size increases with increasing the principal quantum number, or n. So if we want to arrange the following atoms in decreasing order, we would want to start with the one that would be the largest and go to the smaller one. So we would say the largest is going to be lithium, followed by Be, and then finally carbon, lithium, beryllium, carbon. Because they're adding electrons to the same energy level, the effective charge is increasing, causing the atom to decrease in size. Ionic radius is the radius of a cation or anion. Remember, a cation is a positively charged atom because it's lost valence electrons. An anion is a negatively charged atom because it gained valence electrons. So ionic radius affects the physical and chemical properties of an ionic compound. The 3D structure of an ionic compound depends on the relative sizes of its cations and anions. So if we look at the first graph, this is a graph of our alkali metals, or group 1. All of group 1 are metals, so they're going to lose electrons to form cations, which would be the red line. Notice that the cations decrease because they're losing electrons, which reduces the repulsion, so the electron cloud shrinks. But if we look at the halogens in the second graph, halogens would form anions, which is our blue line in the second graph. Anions increase in size because nuclear repulsion resulting in the extra electron enlarges the domain of the electron cloud. In other words, the effective nuclear charge decreases. There's not as much attraction between the electrons and the constant nuclear charge. So if we look at the first picture, lithium is the big gray ball, and then you have fluorine, which is a small green ball. We would notice that if we were just to look at the atoms. But when they form their ions, lithium shrinks and fluorine gets larger because lithium loses that electron, so the nuclear attraction between the nucleus and the electrons increases, so it shrinks. But fluorine gets larger because the effective nuclear attraction is decreasing. So there's a parallel trend between atomic radius and ionic radius. The size comparison is meaningful only if the ions are isoelectronic, which remember means they have similar electron configurations. Cations are smaller than anions. If we have a tripositive or +3 ion, it's going to be smaller than a dipositive or +2 ion, which is going to be smaller than our unipositive or +1 ion. And you can see that if you look at magnesium +2 versus sodium. Magnesium +2 is smaller than just +1. The radius increases when you talk about the negatives. So -1 going to -2 going to -3, we're actually getting larger. So select the smaller ion in the following pairs, K+ or Li+. Well, the smaller one is going to be Li+, and that's because K+ has a naturally larger N value, so it is larger. Au+ or Au3+. The smaller one is going to be Au3+, and that is because it has lost more electrons than the +1. Letter C, you have P-3 and N-3. Well, since phosphorus has a larger N value, it would be the larger one. So N-3 would be the smaller one. So across the period, elements change from metals to nonmetals. From metals to metalloids to nonmetals. So the difference just in between metals, metalloids, and nonmetals has to be taken into account when discussing physical properties. However, when you go down a group, physical properties vary more predictably because you are talking about them being in the same physical state. Melting points, for example, decrease down a group. So if we know the melting point of argon and xenon, we can actually take the average to figure out the middle element, or krypton.